the department, as I think this is the most popular thesis defense since I've been here, which is fitting since Kevin has been one of the most popular students here. And what do I mean by popular? Well, he has not one but three advisors. That's me, I'm Joe Blitzstein, Sam Coe, Jun Liu. This department encourages students to work with more than one faculty, but I take that within limits, and that you can get a little scared if someone starts floating around between too many advisors, or tells one advisor that they're working on the other one's project, and the other way around, and get nothing done. It can get a little scary. But Kevin is one of the few who just kind of seamlessly has been able to handle that and staying on top of several research projects at the same time, as well as doing all these different internships. And he's also been my most popular TF in Stat 110 many times. So that's all really impressive. So it's been a great pleasure having you here for 5 years. Kevin and I also came to the department same year. So
from the same school.
Well, both from Caltech. And okay, well anyway, let's all welcome Kevin.
Thank you, Joe, and yes, thank you to Joe, June, and Sam, who were my three advisors, and it's been a wonderful journey. Thanks to everybody for coming, and to my girlfriend Deborah for bringing lots of food for afterwards. So this is an incentive for you to for you to sleep through the talk and stay until the talk instead of leaving. Anyway, okay, so defense. What do these three pictures have in common? Well, not that much. Can you see what that is on the left? That is a network, a social network. In the middle we have two balls, which are actually brains. Okay. And out here we have some proteins. These are actually small parts of proteins called fragments. Now what's interesting, what these three have in common is that they're all structured multivariate data. They've got the structure imposed on it, and they're also multivariate in nature. What do I actually do with this data? Well, I do a range of things. In the first two columns, networks and brains, what I look at is inferential problems. Those are problems where we try to say, with a certain degree of significance, that those two networks are relatively close to being the same. They come from the same underlying process. And same thing for those two brains. Are they the same or are they different? In other words, we go from data to a model to answer that question. And in the last case, protein folding, I go in reverse. I go from model to data. That's where we try to draw these random loops, which are small chunks of proteins. And I'll explain a little bit more about that later. Now, what will I discuss today? Well, I'll discuss two of these things. There will not be any brains in this talk. Oh, I don't mean what you think I mean. I mean, we will not be discussing brains today. That's why I put a big red X through them. We'll be discussing networks and proteins. So, without further ado, let's dive into networks. And many of you have seen this before, but you can bear with me and not give away the answers to all the noobs. You're about to see 6 graphs, 6 social networks. They represent friendships among 3 different groups of people. One are prisoners, one are assembly line workers at this tailor shop, and the last are these students at a karate club. These are famous data sets. I didn't make these up. They're from the literature. And your tasks are, number 1, to group the graphs into groups. Pick which 2 of them are partners, and out of the 6. Group the 6 into 3 groups. Task number 2 is then to look at those groups and try to label them. In other words, decide which of these categories corresponds to which of the groups. Okay, so here they are.
Oh.
Right. And now I'd like to get some audience feedback here and say, let's first of all tackle the easier question, which is, which of them are partners? Group them into 3 groups of 2 each. Well, let's take the guy in the upper left. Do you know who his partner is? Yeah. Upper partner?
Upper right.
Upper right? Oh, good call. Now, how did you know that? How did you know that, Carl?
That's probably not.
Oh, okay. See, the other ones all look kind of distinctive, right? Like the guy in the lower right here, who's his partner? Yeah, right there. Okay. And what do you notice there? Well, if you notice, they have these big star-type structures that are jutting out at you, and they're pretty distinctive. Okay. So there are 3 distinctive groups, and the last one is the upper middle and the lower left. Those also look pretty distinctive. They don't have as many edges as the other graphs. So those are the groups. That's correct. And now the next question is, which category is which? Which one do you think are the students, number 1? I'll take a stab at it. I love doing this at my job talks and then saying answer. You're wrong.
It will be really.
Go for Martin.
Star graphs are the students.
Pardon me?
Star graphs are the students.
Bingo. All right. Now,
Why?
you may or may not have already known the answer. I won't give it away. But yes, that's absolutely right. So students tend to form friendships with these hubs, these cliques that are in stars. So yes, the bottom two are from the students. And now, what about, which one is the prisoner?
Left.
Yeah, upper left. Upper, did you mean upper left or? Of course you did, right? Yes, and you're absolutely right. So the assembly line workers tend to make friendships among their nearby people on the assembly line. That's why you get that structure in the upper middle. Whereas the prisoners, they meet in the mess hall, they make friends among all the prison gangs, et cetera, et cetera. And we were absolutely, we finally got to the bottom of this. Here they are, prisoners working with students. Now, let's try to isolate the features that caused us to notice that certain of these were partners with one another. So how are they different? Well, number one, compare the orange to the greens and blues. Well, the greens and purples. Well, if you notice there, the big difference is that the orange has a lot more edges. And edge, in case you don't know, is just a link between two nodes. Look, they're a lot more dense with edges than the other two. Now, what about the green versus the purple? Well, there are two things. The green has more triangles, if you notice. If you look closely there, there's some triangles in the green. Now, but if you look at the purples, there aren't as many triangles. Instead, you see these star-type structures. Okay, so there are some. These graph group clusters are categorized by the sorts of geometries that are prevalent. Now, we can then assume, it seems to be a natural assumption, that graphs themselves, observed graphs, arise from a distribution. And the distribution is either, in this case, the orange, the green, or the purple distribution. And where the probabilities of each graph are governed by the prevalence of a certain type of geometry. Edges, triangles, or stars. And the parameters in this model, how we will define them, you will see shortly. But the parameters should impact the prevalence of these sorts of geometries relative to one another. So that's the goal for our graph model. Now, let's try to dig in a little deeper here. If we count the edges, the triangles, and the stars on each of these, then you get these totals here on the left. Now, just to define exactly what I'm talking about when I say an edge, a triangle, and a star, I have this graph here. There you can see an edge is just a link between two nodes. A star is any structure in which you have two buddies, but there's no linkage between the other one. And a triangle is one where there's a group of three linkages.
Which one's the star?
The star is the one right here. Okay, see there, it looks like a kind of a wishbone sort of structure. Yeah. And now, if you notice, actually they overlap, and the triangle does contain three stars inside it. So what's really important is how prevalent these geometries are relative to one another. And I've highlighted the feature in each of these graphs that kind of defines it and says that that's what makes that graph distinct. In the case of the students, it's the stars. That's why there happen to be a lot of them relative to the edges and triangles. In the case of the prisoners, it was the triangles, and in the case of the assembly line worker, excuse me, in the case of the assembly line workers, it was the triangles, and in the case of the prisoners, it was these edges. Okay. All right. So now, what model are we going to define? Well, the exponential random graph model. I know there's a lot of criticisms about this model. We'll discuss them briefly, but the basic idea is that you take these different features you care about and throw them into your probability function. Your probability of a graph is proportional to the exponential of a linear combination of these features and unknown parameters. The unknown parameters, how large they are, governs how likely it is to observe that sort of feature in the graph. Okay. So this is the model we're proposing. Now, more generally, you can just vectorize that beta, turn it into a beta prime times x, where x is a vector of features, and say the probability is proportional to this exponential function. And now, notice too, I used a little fish there. That was for proportionality. That's because, and this is the key point here, that in order to get equals instead of that fish, what you need is a normalizing constant. And that's the nasty part. Okay. Normalizing constant is a function of the parameters, and it happens to be a very nasty function of the parameters. Okay. The fact that it's unknown is going to be very troublesome.
But
let me explain.
In this expression, there must be some constraint between triangles and two stars and so on, right?
Yes, there can't be a certain number of two stars.
Yeah, but do you put a
relative to the number of
constraint in?
triangles. Oh no, I mean, well, it's the support of this distribution is the space of all permissible graphs. Yes. So I mean, in the the space of there's the balance on the number of edges, triangles, and 2 stars is not easy to state. But remember, the data itself is a graph, not the features. The features are actually just sufficient statistics. Okay. All right. So now let me explain why it's such a problem that we don't have this normalizing constant. Okay. So suppose that we want to use maximum likelihood to find estimates of these parameters. Parameters would tell us something about the graph. But unfortunately, in order to perform maximum likelihood, you've got to know that normalizing constant. And unfortunately, you need it to find the MLA. Not only that, but if you were to try to optimize that function, you would need the value of the normalizing constant at several values of the parameter. See, the normalizing constant is a function of the parameter. You need it for all values of that parameter in order to tweak it until you get to the maximum. Okay. Now, because it's a little hard to understand like that, I'm giving a simple example here. Consider the Poisson distribution. Okay. In the Poisson distribution, the probability that x, your random variable, is equal to a number k is proportional to lambda to the k over k factorial. Okay. And that's similar to the way I expressed the graph model initially. But then if you go in and compute the normalizing constant, what you normally do is you want to make it integrate to 1, sum to 1, the probability. So what you say is, hey, add up that function over all possible values of x. In this case, x ranges from k is 0 to infinity. And then in this case, there's an analytic answer, e to the lambda. So it's pretty convenient. You can go back and plug that in, and notice that it's a function of lambda, the parameter. Plug it back into the probability, and then you can perform maximum likelihood. But in the case of graphs, we have no such luck. Why? Well, the space of all possible graphs is ginormous. And if you were to add up that function across all the graphs, then unfortunately that has no analytical form. Not only that, but there are a ton of graphs, so it's not that easy to evaluate. Not only that, but even if you were to go through and gather all the computing resources and evaluate it once, you then have it for one value of beta, which you would then need to do several times on your way to the maximum likelihood estimator. Okay. All right, so just to give you an idea of how these calculations work, I thought I'd give a brief, non-trivial example here. Suppose that we're dealing with graphs of node size 4. So this is a small space of graphs, so you can get an idea of how the calculation works. Well, consider the types of unique graphs here. By unique, I mean unique up to an isomorphism. So if you take, for example, the second graph from the second graph down on the left side there, notice that the number of isomorphisms is 6. Why? Because I could put that edge and put it between any other pair of nodes and get effectively the same graph. And there are 6 possible pairs there from 4 choose 2. So there are 6 isomorphisms there, but every one of those graphs has the exact same feature set, which is 1 edge, 0 triangles, and 0 stars. Now, what you then have to do is, for every possible graph here, is take the dot product of your parameter vector beta with the features, and then you evaluate beta prime x for every one of these graphs. You then go and add them all up, and now you have it for 1 beta. Okay? You have to do this several times. So even for 4, it doesn't seem totally trivial. But for large amounts of nodes, or even medium amounts of nodes like 20, look, I mean, I even had to go over to another line to express how large this integer was. The cardinality of the set of graphs, which is the number of possible graphs, there is a ton of them, because there are 20 choose 2 possible edges. Each one can either be on or off, and there are 2 to the, so that means 2 to the 190 total graphs. That's a lot. That's a lot. It's already become an intractable problem. Okay, so instead, if you notice there, though, that sum, that normalizing constant, is actually just a sum. And because it's a sum, you can approximate it using sampling methods, which is the beautiful thing. Any sum, like a mean, for instance, is a sum. It's a sum divided by n, but it's still a sum. And you can approximate that by sampling things and taking the sample average. And so we can use that same kind of logic here. And let's say that we have some graphs that are sampled from, sorry for the notation here, but bear with me, it is kind of illuminating. Sample graphs from a fixed parameter value, beta naught, and we sample them from probability of beta naught, and then we first start by writing the exact formula for the normalizing constant, the sum of the exponential over all these graphs. Then take that expression in the sum and divide it in the multiply the top and bottom by c of beta naught. Okay, bear with me, you'll see why later. That's just algebra, and then we see next step is to plug in c of beta naught, plug it in for the exponential function divided by the actual probability of a graph. And what I did there, by the way, is called importance sampling because through the